Hi, my name is Sarah Saraswatula, and this is my report on Lab 3 Magnetic Field of a Bar Magnet. The purpose of this lab is to understand the distance dependence of the magnetic field due to a small bar magnet. The formula for the magnetic field of a bar magnet derived from the Biot-Savart law will allow for us to determine the distance dependence and the magnetic moment. Before we collect data to calculate for these values, we must first compensate for the Earth's magnetic field, which will superpose the bar magnet's magnetic field, yielding a net magnetic field. To do this, I use the Tesla meter application to determine the net magnetic field when the x component is 0 Tesla. To ensure there is no other interfering external magnetic fields, I use the magnetic field calculator to determine the net magnetic field at my location. The net magnetic field at my location is 49.202 microtesla, whereas the application was reading values within a range of 47.4 and 51.2 microtesla. I then located the sensor to be an inch down from the top vertically and a half an inch across from the left side horizontally. After compensating for the Earth's magnetic field and finding the location of the magnetometer chip, I took the necessary measurements in order to determine the distance dependence. The setup for the experiment is shown to the left, with the meter stick oriented such that the magnet's on-axis field and the Earth's magnetic field are orthogonal to each other. I would bring the magnet closer to the magnetometer until it read the required x component magnetic field values of 20, 70, 120, 170, and 220 microtesla. This procedure was performed 3 times for each value, with the data as shown on the chart to the right. This chart also presents the average distance and magnetic field x components. The table shows the average R and average magnetic field x components at each magnetic field value and the corresponding natural log of each value. The natural log of the average distance R and the magnetic field Bx were graphed as shown to the right. The slope of the line, which is the distance dependence, was determined to be negative 0.6908, while the intercept, which is the natural log of the constant k, is negative 10.36. The negative distance dependence indicates that the magnetic field decreases as the distance increases. In order to determine the magnetic moment of the bar magnet, I had to set up the experiment as shown in the lower left-hand corner. Dperp is the distance at which the magnetometer reads 100 microtesla. Dperp was measured to be 0.138 meters, from which Excel calculated the value of D to be 0.195 meters. This value for D was substituted in the magnetic field of a bar magnet formula to calculate for the magnetic moment, which was 5.41. When modeling the system on GlowScript, it was first necessary to include physical constants as shown above. I then created a cylindrical object to model the bar magnet. The magnet axis attribute, when multiplied by the magnitude of the previously calculated magnetic moment, derives the value assigned to magnet.mu. I then created a dipole B function which calculates the magnetic field of the bar magnet given 2 vectors, magnetic moment and distance. Afterwards, I began to model the 2 arrows on the same axis as the bar magnet. This was done by first calculating R-axis for each arrow, given the bar magnet position and the observation location. The B-axis is calculated by using the dipole B function with the corresponding R-axis and magnet.mu inputs. The arrows are then modeled with the position being the previously determined observation location, the axis being B-axis. The process for calculating and modeling the magnetic fields at observation locations perpendicular to the bar magnet is the same as for on-axis, except the 4 observation locations are on the positive and negative y and z axes. The distance and magnetic field vectors are assigned to the rperp and bperp variables. Once again, the process for calculating and modeling the magnetic field on the 45-degree axis relative to the bar magnet is the same. I chose to model the magnetic field at 4 different observation locations at 45 degrees, 135 degrees, 225 degrees, and 350 degrees, with the x and y components being variations of the positive and negative dperp, while z remained 0. This image shows the final output model and values. The computational value of D is 0.195 meters, which is the same as the mathematically derived value. In this experiment, we wanted to understand the distance dependence of the magnetic field due to a small bar magnet. The physical principle exemplified in this experiment is the magnetic field of a bar magnet derived from the Biot-Savart law, which allows for me to determine the distance dependence and the magnetic moment. In performing this experiment, I made 2 observations. First, that as the magnetometer gets further from the bar magnet, it detects a near-zero magnetic field in the x direction. Second, as the magnetometer gets closer to the magnet, the x component of the magnetic field increases. I also determined the value for the distance dependence to be negative 0.6908. Theoretically, this value is negative 3, as indicated in the formula for the magnetic field for a bar magnet. After performing this experiment several times, I've gotten the same value each time. A reason for this difference could be that I was unable to remove all other materials in the environment that could have interfered with the magnetic moment. I calculated the magnetic moment to be 5.41 and dperp to be 0.138 meters. These values allowed for me to model the system on GlowScript and resulted in a computational d value of 0.195, which is the same as the calculated value. 2 questions arose when performing this experiment. The first is, what if you hadn't oriented your experiment to compensate for the magnetic north and had instead laid out your meter stick at some intermediate angle with respect to the Earth's magnetic field? How would your results have changed? I said that the net magnetic field measured by the magnetometer is the sum of the Earth's magnetic field and the bar magnet's magnetic field. By doing this procedure, Earth's magnetic field becomes 0 Tesla, and the only detected magnetic field is that of the bar magnet. Otherwise, we would have to adjust for Earth's magnetic field, whether it be an increase or a decrease in the value. The second question is, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? I said that I would expect the magnetic field to increase, but not necessarily double in magnitude.